In this lecture, I will talk about controller design using root locus. So far, we have seen different methods to design a PID controller. Here we will see another method to design a controller in general. It's not necessarily a PID controller, but also this method is applicable for designing a PID controller. So basically, it's a general method, it's a general approach for designing a controller. As I said, it might end up having a PID controller as a controller, but it could be also other types of controller. But before talking about this method, I'm going to introduce you a new rule applicable for some systems for drawing root locus. So an extra rule for root locus. Why I didn't mention that when we were talking about the root locus, because usually this rule is not that useful for drawing. It is useful for analyzing a root locus. That's one reason, and the second reason is that it is not applicable to all systems. It's only applicable to the systems that they have at least 2 more poles than zeros. So only applicable if n is greater or equal to n plus 2. And what is n? As we have seen before, n is the number of loop gain poles, and m is the number of loop gain zeros. We can use this rule if n is greater or equal to n plus 2. So as I said, it's not applicable to all systems. That's one reason. And actually, this rule you cannot find it in any of the books I have introduced you. In the 2 books I have recommended in the curriculum, but it is not something that I have invented. You can find it in the literature in other books. But the way I use this rule is mostly for designing a controller, not for drawing root locus, because as I said, it's more useful for analyzing root locus, not for drawing. Okay, what this rule says, according to this rule, the summation of closed loop poles is always a constant value. Summation of the closed loop poles is always a constant value. Remember, this rule is only applicable if you have at least 2 poles more than zeros. So in that case, the summation of closed loop poles is always a constant value. Before I explain it any further, I can give you an example. In the example, suppose that the loop gain kg of s, h of s, is equal to k divided by s plus 1, s plus 2 multiply s plus 3. So suppose that you're going to draw the root locus for this system, and the number of poles, the number of loop gain poles is 3. Loop gain doesn't have any zeros, so basically n is this condition is fulfilled, so you can use this rule. I will draw the root locus roughly. I will draw the root locus. So we have an open loop pole here at -1, another one at -2, and the third one here is at -3. And if you remember from root locus, this part is part of the root locus between -1 and -2. Also here is part of the root locus. So this pole is one of the closed loop poles is moving to the -infinity on this line, and these two actually meet somewhere in between, and then we of course have two asymptotes, one 60 degrees, another one -60. The third one, by the way, the third one is also 180, but these two, as I said, they will converge to those asymptotes. I don't draw that. You don't need that. The focus here is on something else. Okay, that's the root locus. But we know that when k is equal 0, the closed loop poles are the same as the open loop poles. So for k is equal 0, I will I write k equals 0 on top of the poles. Then we know that the closed loop poles when k is 0 is here. So if k is 0, k equals 0, summation of closed loop poles. Okay, what is the summation of closed loop poles when k is 0? Because as I said, when k is 0, the closed loop poles are the same as the open loop poles. So the summation of the poles would be -1, -2, -3, which would be -6. So the summation of closed loop poles when k is 0 is -6. And this -6 would be the same for any other value of k. You know that when we increase k, the closed loop poles moves from -1. One of them moves from -1, goes to the left, and then it leaves the real axis. And at some point, actually, it crosses the j omega axis. So for some values of k, if we name it k1, so one of the poles is here, the other pole is here, so it's the same k we have here. And the third pole, because when you increase k, as I said, one of them is coming here, the other one is going here, and the third one is moving to the left. But can we specify for k is equal k1 where the third pole is? So if k is equal k1, then the question is, where is third pole? Where is the third pole? The third pole. We know that two of the poles are on the j omega axis. One of them here, the other one here, and they are symmetric about the origin. And the question is, where is the third pole? Now this rule helps for finding the location of the third pole, because we know that the summation of the poles should remain -6. So if we have two poles here, so for k is equal k1, one of the poles, for this value of k, one of the poles, S1 is plus j omega, S2 is minus j omega. We don't know what omega is, but some omega, let's name it omega 1 or omega u. If you like to name it omega u, you can name it omega u, because usually this cross this cross frequency, we name it omega u, the ultimate frequency. We can also change it to ku if you want to use the same notation as we had. So one of the poles is at plus j omega u, the other one is at minus j omega u, the third one we don't know where it is. Okay, but there's one rule that I haven't used, and this is this rule. We know that the summation of poles should be minus 6. So summation of poles in this case, S1 plus S2 plus S3, we know that it should be minus 6. And the interesting point is that S1 and S2 will cancel each other. And what we get is that S3 is minus 6. Okay? As I said, this rule, this extra rule, it didn't help in this particular case. It didn't help for it didn't help for drawing the root locus. It did help for finding the place of the third pole when two poles are on the j omega axis. So is there any way, because we have the third pole position, can we find k now? Or can we find the location of the other two poles? Can we find omega u? The answer is yes. Actually, we can find, but how to find it? To find this part of the solution, actually, it doesn't have anything to do with this extra rule. The part I wanted to show you how to use the extra rule, actually it is finished here, but to continue this example, and maybe this last part is also useful for you, I will find omega u and ku for you, but as I said, it is not related to this extra rule. The application of extra rule was to find this the third pole when two poles are on the j omega axis. Anyway, to find the position, or to play the place of the other two poles to find the place of the other two poles, I mean these two the two poles that are crossing the j omega axis, we can find, or we can form, the characteristic equation. What was the characteristic equation? If you remember from some lectures before, and we call that delta S, and delta S is 1 plus loop gain. 1 plus loop gain is equal to 0. So 1 plus kg h is equal to 0. Why this one gives you the characteristic equation? Because this is the denominator of the closed loop transfer function. And the characteristic equation is an equation that gives you the closed loop poles. If you set it equal to 0, it will give you the closed loop poles. We talked about that before, that to find that we can set the denominator of the closed loop transfer function equals 0. When we have the loop gain, we can simply write this. So it is always like that. Therefore, if you do that, we have 1 plus k over s plus 1 multiply s plus 2 multiply s plus 3 is equal to 0. And if you do this common denominator, then you get s plus 1 multiply s plus 2 multiply s plus 3 plus k is equal to 0. This is the characteristic equation, and what we are interested in is to know what happens to the other two poles of this equation when one of them is minus 6. So you know that it is a third order equation. So a third order equation, it has three poles, three roots. A third order polynomial has three roots, and we have one of them. We are interested to know the other one. So always you can divide this higher order polynomial by s plus 6, because s plus 6 is giving you one of the roots. You can divide that. But if you want to divide that, you should have k. So how to find k? You can substitute s3 equal minus 6 or s equal minus 6 and find k, and the k you will find is ku. So if in this equation, if you set s is equal minus 6, you want to know for what k one of the roots of this equation is minus 6. So if you set s equal minus 6, therefore you have minus 5. I'm substituting minus 6 here. Minus 5 multiplied minus 4 multiplied minus 3 plus k is equal 0. And basically, if you take that one to the other side, then you have 5 multiplied 4, which is 20, multiplied 3, which is 60. Therefore, k is 60. And remember, this k is ku. So I could have named that here ku because I have substituted s equal minus 6. And I know that when one of the poles is minus 6, the other poles are on the j omega axis. So this one is ku. So we could find ku, and the question is, where are the other two poles? So what you can do, you can divide the characteristic equation by s plus 6. It will give you the other two poles. So the characteristic equation, if I form that, so if I substitute 60 here, s cubed plus 6s squared plus 11s plus 66 is equal to 0. How I calculated that? I just substituted k is equal to 60 here, and then multiply these terms out. This is what you get. And if you divide this polynomial by s plus 6, what you get, the other two poles are s. So if we divide this polynomial by s plus 6, we would get s squared plus 11, which means that the other two poles are the roots of this polynomial, which means that s1 is j square root of 11, and s2 is minus j square root of 11. So one of the poles has been at minus 1, the other one was at minus 2. So these two poles have moved to the right. One of them is at plus j omega, the other one is at minus j omega, so the summation is 0. So the two poles together have moved 3 units to the right. Okay? One of them 1 unit, the other one 2 units. So they have moved to the right 3 units. It means that the other pole should have moved to the left 3 units. So because of that, the third pole, if you move the third pole from minus 3 points, 3 units to the left, it would be minus 6. That was the main result here, because we will use that when we design a controller. And also I continued the example. I calculated the other two poles, the ku, and some other things that you could see. One important thing that I also use in this example, when you have one of the poles, one of the closed loop poles, and you want to find the gain such that the closed loop pole is at that point, at the specific point, what you can do, you can form the characteristic equation and then set S equal to the value you have, and then you can find K. So we will use this method many times from now on.